Medic Paths, yet again, welcome to our IGCSE Chemistry class today. We'll be teaching compounds and mixtures. So just to introduce myself, if you haven't seen me already, my name is Ayano, and I'm a fourth-year medical student studying at King's College London this year. Okay. Before we begin, just want to run through the lesson. So it's going to be 2 hours long with a 10-minute break in the middle. Basically, we sort of have sections in our classes. So we go through the theory, some foundations, make sure you definitely nail those basics for each bit. And then we'll go through some real past paper exam questions and some quiz questions just for some extra fun. All right. So do stick around. And we'll be doing this all on Mentimeter. So if you guys want to get ready as I get through the class, today's code, you can go to www.menti.com and the code is 32260827. Don't worry, I'll come back to this later if you're not ready. Again, 32260827. All right, so I'll show it again when we come back to it later. Okay, so today's key objectives that we're going to go through, sort of like the subtopics, are compounds, purity, and mixtures. Looks fairly straightforward, but we do have quite a bit to go through. So these are the learning outcomes as usual, and we'll be taking through these as the lesson goes along. And you can take a look at these after the class. You will get the slides and the lesson recording sometime next week. Okay? So let's head back to Menti now. We're going to start with the classic, how confident are you question in these three areas? So how well do you know what compounds are and mixtures are? Do you know what the differences are? And what do you know about purity? We will also be covering a little bit about solubility today as well. Okay, because it's very relevant to mixtures. So if you just get your phone or computer out again, go to Menti and let's see where you guys stand. We highly encourage you to answer all the questions today. Always try to answer everything. Even if you don't know it, just make the best guess you can. And even if you really can't make a guess, just choose something, because you will have to do that in your examinations anyway. Hopefully you don't encounter a question where you just completely cannot answer, and that's why we're here, to make sure that you get your basics down, so that even if you can't remember everything for your examinations, if you have your basics, you can still work things out. Okay. Looks like everyone is sort of average, sort of confident over here. Okay, that's fine. Perfect. Hopefully we get you guys to above 4 and as near to 5 as possible today. If not, again, you will have the lesson materials after the class. All right? Okay, let's move on. So today's first subtopic is compounds. Okay, so last week we went through atoms and elements, and the week before we went through states of matter. So both of these things, those lessons are going to appear today again, just as a sort of recap, and because everything is basically linked together. So we talked about elements last week, and we talked about how to sort of read them off the periodic table. In the following weeks, we'll look more at the periodic table, but basically elements are represented by chemical symbols, right? As you might see on the periodic table, and there's some numbers that you need to know. So just a reminder, the mass number, there's a mass number and an atomic number. So the numbers might be switched around when you see these elements, but not to worry at all. Just one is always going to be bigger than the other. The mass number, if you remember, is made up of protons plus neutrons, okay? And the atomic number is also called the proton number. All right, and electrons are not involved in the mass number because they're very light, and in atomic number is called proton number, so we're just looking at that, okay? And just from these two values, you can work out the number of protons, the number of neutrons, and the number of electrons, Okay, so yep, that's what I said. So for example, you might see this in your periodic table. Don't worry, you will never have to remember or memorize these things because you will get the periodic table in your exams. But obviously, I think once you do a lot of practice with papers and everything, you will eventually remember that, oh, this element has this symbol, etc. Okay, but don't worry about it. Most of them are very similar to their names. So helium is the first two letters, He, lithium, Li, but sodium is a bit more special. It's Na, and so on and so on, okay? Now, so that was just a recap, chemical formulas for elements. Now we're going to look at molecules. So we also went through this last week. We touched on it briefly. So we just want to make sure that you know the difference between molecules, and later the next slide is going to be on compounds, okay? So we're sort of getting to looking at the different definitions here. So molecules are basically names for non-metal elements that exist as the way they are naturally. So they're made up of two or more atoms of the same element. Okay, so non-metal elements with two or more atoms of the same element chemically bonded together. Okay, for example, on the right-hand side, we've got hydrogen, that's H2. So hydrogen exists as H2 molecules. Okay, you don't see just H atom floating around in the air. So to write these, it's followed by a subscripted 2, which is basically like this. So for example, bromine is, I believe, gas or liquid at room temperature. And basically you subscript the 2, which basically means to make the 2 a small and at the bottom. Okay. Chlorine also exists as 2 atoms bonded together, and oxygen as well, the one that everyone knows. So they're all non-metal elements. Okay, we're going to look at more at what non-metal really means in the periodic table next week. But yeah, so these all exist in this way naturally. And of course, oxygen is O2 as we all know it. Another way you might call them is diatomic molecules. Di means 2. Atomic refers to atoms, so 2 atoms, right? And again, I want to stress that it is the same element, okay? 2 or more, okay? Doesn't have to be 2. Okay, next, compounds. So now this one's a bit different. Look over here. It says it's made up of 2 or more, okay? That's the same. But now it's different elements chemically bonded together, okay? So the chemical formula for a compound shows symbols for each element in the compound and the number of atoms of each element in a unit of the compound. So for example, let's look over here. I wonder if you guys can recognize what this is. It's very vague, but basically molecule might look like it's water. So as you can see, all water is made up of is made up of H2O compounds, okay? So you can see that there's 2 different elements involved. There's a hydrogen and there's oxygen. Now this shows the number. So this is always on the right-hand side of the element that is referring to. So there are 2 hydrogens and 1 oxygen involved, okay? So So with compounds, there are 2 broad categories to know, ionic and covalent. We will cover more on these things in chemical bonds later on, okay? But just to touch on them today. So ionic compounds is basically when there's a bond formed between 2 different atoms where electrons are transferred from one atom to the other. Okay, don't worry too much about this terminology. If you have not learned about ionic bonds and compounds yet, not to worry. This is just a definition we're going to put here as a good introduction to later on. Okay, so they have ionic bonds. Ionic compounds have ionic bonds between the atoms, and usually ionic compounds, it says 2 different atoms, right? Between 2 different atoms, and so the 2 different atoms are metal and a non-metal. It's always between these 2. Okay. For example, sodium has one electron in its outer shell, which we did look at last week in atoms and elements, okay? And when it wants to form an ion, basically, so let's say we have a sodium ion here, and if we just draw the valence shell, which is the outermost shell, there's basically one electron. And remember we said elements want to be stable. They want to have a stable configuration, right? They want to be in a stable state. And in order to do that, they want to have a full shell. So there is a full shell underneath, but we don't need to draw all that. We only want to draw the outside usually, because it will be too many to draw once we get to the big elements. So in order for sodium to become more stable, it wants to lose this electron. Okay, if it wants, it can also maybe gain 7 more in this outer shell, because remember 8 is the maximum, right? But gaining 7 more clearly sounds like it uses a lot more energy than losing one, right? So it will lose one and will form an ion. An ion is basically a charged atom. Okay, that's not quite right, but basically an atom has no charge. And when there is a charge, which is basically when an electron is added or lost, then an ion forms, okay? For sodium, it loses an electron, so in the end, you've got more protons than electrons, so it looks like an Na+, okay? It likes to be an Na+. Now, there's also something called compound ions. So just now we looked at a simple ion over here, like Na+. Compound ions are basically some common ions which contain more than 2 or more elements combined together. So for example, you might have heard of things like sulfate, carbonate, nitrate, etc. So you can see sulfate has S and O, so sulfur and oxygen included. Nitrate has N and nitrogen and oxygen, right? So this charge over here, for example, let's look at ammonium, okay? This positive charge is referring to the entire NH4, okay? So this, just imagine that this is 1 unit and there's a plus charge on this entire thing. It's a more complicated, it looks quite complicated, but just imagine this as 1 unit, okay? Sulfate as well always has a 2- charge. And these are unfortunately things that you just have to remember just like that. But with practice, you'll become a natural at it. So the formula of an ionic compound can then be predicted using the formula of its ions. The number of ions in a formula must give an equal number of positive and negative charges. So do we have... So let's think of an example over here. So magnesium, for example, often likes to lose 2 electrons, so Mg2+, okay? You just need to know that. We can there is a way to figure this out, but we'll go through that next week in periodic table. And over here we have, let's say, carbonate, okay? This whole unit has a charge of 2-, okay? So the number of atoms is subscripted and the charge is superscripted, okay? This is always like this. Superscripted means on top, subscripted means it's put at the bottom. So this has a charge of 2+ and 2-. If you put these two together, basically, it will form magnesium carbonate like this. That's how you would write it. And overall, the 2+ and 2- will make it have an overall charge of 0, right? I hope that makes sense. So that's what these paragraphs are referring to, okay? Covalent compounds. So we talked about compounds in general, and then we said there were ionic and covalent ones. So we talked about ionic just now between a metal and non-metal. Now covalent compounds are when a bond is formed between atoms of 2 or more different non-metals. Okay, just now was metal and non-metal. Now it's between 2 non-metals. Again, we'll cover this again later. Again, covalent bonds and between non-metals. So examples like carbon dioxide, C and O2. Okay, so these aren't charges that we're talking about. They're both non-metals. Water is also an example of a covalent compound. Methane, if you know it, CH4. If you guys know, a big source of methane in our atmosphere is actually cows farting. And ethanol, so like a type of alcohol. Okay? So let's look at some chemical and word equations now. So chemical reactions are basically reactions where there are 1 or more reactants that form 1 or more products, okay? We'll look at this terminology in a moment. Basically, these reactions can be written in words or as chemical formulas. So let's compare these two. You might be asked in exams to write either one, okay, based on the question. So you need to know them both. For example, if we have a word equation, sodium plus chlorine, okay, and if they react together, they will give sodium chloride, okay? So you just sort of have to learn that the names are like this. So the reason why, so the word sodium remains the same, but chlorine and chloride, there's a slight change in name. So chlorine, okay, so sodium occurs like this, Na, okay, and then basically chlorine is in this form. And the reason why it's chloride means that basically this thing has a charge, okay, so it's in this form. So chlorine refers to Cl2, whereas chloride refers to Cl-. So as we're going to see in chemical equations over here. So this is a balanced chemical equation. So notice the differences between word and chemical equations, okay? So chemical equations firstly has state symbols as well. So this is, remember we talked about states of matter in the first lesson. So we'll see that in the next slide. But basically, you might be asked to write state symbols in word equations as well. So it all depends on the question, okay? If it doesn't state it, you may or may not need to write it, and it might not. It probably won't cost you a mark if you don't write it, and if the question doesn't say to do so, okay? So yeah, like I said, so chlorine refers to Cl2 specifically. Chloride refers to a chlorine ion, okay? So another example, hydrogen plus oxygen to make water. Hydrogen plus oxygen makes water. So the reason why we put state symbols is so that we know that hydrogen exists as a gas normally, oxygen exists as a gas, and it will give us a liquid water, okay? So you also notice that there's some numbers in front of these chemical symbols and formulas. Now this is showing the number of units. So there's 2 sodium atoms plus, if there's nothing in front, it just means 1, okay? 2 sodium atoms plus 1 chlorine molecule, okay? Let's use the right terminology, gives 2 compounds, ionic compounds, right? So this is referring to the entire thing, okay? Whereas remember, this number is referring to just the elements right before it. Okay, let's look at how to balance chemical equations because this might take some time. So first, you might be asked to write an equation. For example, let's use hydrogen plus oxygen gives water, like we saw just now. First, you want to write the equation. Okay, don't care about balancing. Balancing refers to putting the number of units in front because basically, it's like the law of conservation. If you look over here, if we didn't put the units, you would end up with 2 hydrogen atoms, 2 oxygen atoms gives 2 hydrogen atoms and 1 oxygen, which doesn't make sense. Like, where did the oxygen go? So it's not that it disappeared, it's just that the equation's not balanced, right? So first you write the equation that's unbalanced, don't care about the numbers, okay? Just want to figure out what are the reactants and what are the products. Reactants are basically the stuff that come before the arrow. This is stuff that react together, okay? Pretty straightforward. And products are the stuff that are produced. Okay. Next, you want to include state symbols if you have been asked to. So you know, so solids are written as S, liquid as L, gas as G, and aqueous as AQ. So aqueous is quite special. Basically, this is when something is dissolved in a solution. Okay. I think we'll see an example later. Whoops. Okay. Something is dissolved. Okay. Now, finally, the last step would then be to balance it. So, balance the equation by determining the coefficients that provide equal numbers of each type of atom on each side of the equation, and they're always in whole numbers. We could write them in fractions, but we are not going to do that. We like whole numbers. Okay, it's just so much easier to look at rather than half, 1/4, 1/8, right? Now you could do that if it helps with balancing equation. As long as in the end you end up with whole numbers, that's fine. So we just went through this. So first line over here is an unbalanced equation. Second one, then we wrote in state symbols, okay? And say symbols wise, you just sort of have to remember after a while that, oxygen exists as a gas in our atmosphere. This is all at room temperature usually. Okay, and balancing it. Okay, so if we look at the first one over here, okay, ignore the last one. It's already been balanced. So it's hard to tell. So let me explain how we get to 2 hydrogens plus 1 oxygen gives 2 waters. Okay, for those of you who have not done this in class yet, so we see after we write the unbalanced equation that there is less oxygen on the right side than on the left. Basically, everything on the left should equal to the number of atoms on the right, okay? So to make the oxygen the same, because the hydrogen is already the same, right? So we're just going to change the oxygen. So let's put a 2 in front here. Sorry, okay. Let's put a 2 in front. So now you've got 2 oxygens on the right and 2 oxygens on the left. That's perfect. But now you have 4 hydrogens on the right and 2 hydrogens on the right. So we need to balance that. So how do we do that? By adding a 2 in front. You do 2 times 2, yeah? 4 hydrogens, and now you've got 4 hydrogens, okay? You've already balanced the oxygen, so now that's why it's equal. Hope that makes sense, yeah? Now, relative formula mass. This is basically, we looked at relative atomic masses before. Okay, we saw basically you can find it in the periodic table. It's the mass number we were looking at. So now relative formula mass refers to basically when you're adding up all the atomic masses of each element in a formula. Okay, we'll look at an example in the next slide. To calculate MR, it's called formula mass refers to can be written as MR for short, and relative atomic mass can be written as AR for short. Okay, so to calculate relative formula mass, you want to work out how many atoms of each element there are in the chemical formula, then add up all the AR values. It should be that simple. So for example, we've got carbon dioxide. How do we calculate the MR? So I'll just give you guys 10 seconds to think about it. Okay, but basically it's given here. You usually look at the periodic table for this, but of course I'm just going to give it to you. So carbon dioxide is written as CO2. So one carbon atom has a relative atomic mass of 12, and one oxygen atom has a relative atomic mass of 16. So what is the relative formula mass? Remember, relative formula mass is the addition of all the relative atomic masses. Okay? Alright. Don't need to get the final answer as long as you were able to plug in the numbers. So MR of CO2, basically, so you got 1 carbon atom and 2 oxygens. So 1 carbon, 1 times 12, okay? And 2 times 16 for the oxygen, okay? So the carbon is the oxygen. And basically that equals 12 plus 32 and...
Tak sangkut. Tu lepas dah.
The final MR is 44. Okay? Great. So everyone head over to Mentimeter. This time we put some of the exam questions in the quizzes so that everyone can try answering more interactively. Alright, so the first question we have is, what is the name of the compound with the formula MgBr2? Now we haven't really talked about names, but we did cover it very slightly. So if you guys can try to sort of make a guess with this, if you can. Again, menti.com, code 32260827. Okay, we got most people saying magnesium bromide. Some saying magnesium dibromide, and then we've got some saying magnesium bromine. Alright, and the answer is magnesium bromide. So congratulations to the 83% of you now. So magnesium bromide is the answer. So just to quickly let you guys know, so this is an ionic compound, okay, because magnesium is a metal and bromine is a non-metal, all right? So they are ionic. It's ionic. Mg has a charge of 2+, whereas one bromine ion has a charge of 1-. Okay, so to balance it out, you need 2 bromines to 1 magnesium. Okay, so it's 2+ and 2-. Now, remember we talked about an example just now with chlorine and chloride. So chlorine exists as Cl2 molecules. Chloride refers to the ion, okay? Chlorine is referring to the molecule. Chloride is referring to the ion. Bromine is very similar. It's also very near the chlorine molecule on the periodic table, okay, which is how we figure these things out. But basically, bromine, okay, Br2, it exists as Br2 molecules, all right? But when it's charged, it's called bromide. Okay, so that's why it's magnesium bromide. Okay, now dibromide, magnesium dibromide sounds like a very good answer as well. But unfortunately, that's just not the way that it is answered. We will be using things like di and tri later on in different kinds of naming stuff. But in ionic compounds, there's no need to say dibromide. You just say magnesium bromide. Okay, and I explained why it's not bromine. So next. Don't worry, we got many more questions to go through. How many different types of atoms are in one molecule of a substance that has the formula N2O4? So unfortunately on Menti, we cannot super and subscript. So basically the 2 and 4 should be small, okay? This is one whole compound on its own. How many different types of atoms? Okay, read the question carefully. How many different types of atoms are in one molecule of this? Okay, so the wording is not quite right. This should be one compound if you want to be really specific. So a lot of the time, these words are interchanged, molecule and compound. So they can be not most of the time, but if you're looking at the specifics, there are differences, okay? Because these days molecule is just sort of used in a very general term. Okay, so we got a lot of people saying 2, some people saying 6, some saying 4, and the answer is, again, the majority, great job, the answer is 2. So the reason is,
dia pergi depan tu dia cari ya bomo aku pergi jumpa bomo ada orang tanah bahagian depan.
Oh, hebat. Depan rumah
that's
dia.
because the question says different types of atoms, okay? So N2O4, what are the different types of atoms? We've got nitrogen and we've got oxygen, and those are your 2 different atoms. Okay, so that's why it's 2. This was a tricky one. So 4 isn't quite right. That was sort of a trick one put there. But 6. Now 6, you guys definitely put that there because 2 nitrogens and 4 oxygens. But the thing is, we're looking for different types of atoms. We're not asking how many atoms there are. We're asking how many different types. Okay. So this is just a case of really reading the question carefully. All right. Next up, now this one's a bit tough. Give you guys a bit of time for this. So you guys don't really know what this is, but okay. So basically, this you don't need to know the names of these. Okay, this equation has already been put here for you, and it's unbalanced. All you need to do now is just balance it. Oh, we got some pretty quick ones here. It might help to write down on a piece of paper and try this out, okay? So remember, all the atoms on the left must balance with the atoms on the right. And I will go through this with you guys. Okay, we got a spread of answers. If you've already submitted your answer, try going at it again. Make sure the number of carbons on the left is equal to the number of carbons. I'll give a bit of a tip if you are a bit stuck. So there is an oxygen molecule on the left-hand side, and on the right-hand side, notice that oxygen comes out both times, 2 times, okay? So make sure, now remember, you got to add it all up. So all of left equals all of right, okay? So hopefully you guys didn't miss that. even if you think, I'm not sure if you can change your answers, but if you can't change your answers, not to worry, just write down the question again and try to figure out what the real one is, okay? It doesn't matter whether you actually got the question right on the quiz here. If you can figure it out before I go through it, that is still the same thing, okay? Very wonderful. Okay, looks like we got a close fight between 332 and 534. Oh, okay, so pretty equal. So, and the answer is 534. All right, okay. This was a tricky one. Let's go through this. So, we got C3H8 on the left and some number of oxygens giving some number of carbon and some number of waters, okay? Just to let you guys know, this is called a combustion reaction, but don't worry, we'll cover this in a later lesson. But if you guys know what that is, this is what it is. Combustion is basically when, basically something reacts with oxygen to give carbon dioxide and water. Okay, it's a very typical reaction. So, let's balance this. So let's start with, okay, so let's count first, carbons, okay? We'll deal with the oxygen last because it's the most complicated. As you can see, you don't know how many is on the left and you don't know how many is on the right. So let's start with what we do know first. So, actually, let me see if I can, okay, let's do it here so that I can show you guys, all right? So, because this is really important. You can get tons of practice with this, okay? C3H8 plus some number of oxygens gives some number of carbon dioxides plus some number of waters. Is that right? Let me check. Whoops. Yeah, okay, so let's start with what we do know. So carbons, we have 3 carbons on the left and no idea how many on the right, but basically there's only one compound on the right that has carbons. So let's start by balancing the carbons. So we've got 3 carbons on the left, we want 3 on the right, okay? This is a work in progress thing, it's not the final answer, okay? Next, let's look at hydrogens. We've got 8 hydrogens on the right, and hydrogen only appears one time over here in the water. So we want to balance that in order to, and you know it exists as H2 in this case, within the H2O molecule. So you cannot change this number up here. You can only change the number in front. So to get 8 on the right side, you do 8 divided by 2, okay, and you got 4. Okay, great. So we balanced the carbons, we balanced the hydrogens. Let's move on to the difficult one, oxygens. So now that we have these numbers, let's count how many are on the right because we sort of know them, okay? So in the carbon dioxide, we have 6 oxygens, 3 times 2 equals 6. And on the right, we have 4 times 1 oxygens is 4. So in total, we've got 10 oxygens on the right. Over here, now, O2, okay, oxygen exists as O2. So 10 divided by 2, okay, right? You need 10 on the right, so you need 10 on the left, okay? There's no other oxygen in here. So 10 over 2 equals 5. And therefore, the answer is 5, 3, 4. And you can always check again. 3 carbons on the left, 3 on the right, 8 hydrogens on the left, 8 on the right, and 10 oxygens on the left and right, okay? So the answer is 5, 3, 4. I hope that was a good explanation for you guys. Next, which is or are the reactants of this equation? So you've got HCl, okay, this is not an I, it's a small l. Hydrochloric acid, basically, plus sodium hydroxide gives sodium chloride plus water. So you don't really need to know how I got this equation or anything like that. Just know, the question is what are the reactants? So what's the answer? You can choose more than one. Yeah, tip for you guys, there is more than one answer. So which ones are the reactants?
Ang tali lagi, ari na ari. Hatching dah lagi.
Remember, there's 2 terms we need to know, reactants and products, okay? In a chemical reaction, you always have both of them. You have something reacting together to produce something, okay? So the words aren't anything too... All right, let's stop here. And the answer is hydrochloric acid and sodium hydroxide. So basically the reactants are the stuff reacting together. So usually it's on the left side of the arrow, okay, the tail end of the arrow. So hydrochloric acid is reacting with sodium hydroxide to make sodium chloride and water. So hydrochloric acid and sodium hydroxide are the reactants, whereas sodium chloride and water are the products, okay? So the first two are making the next two, okay? What's next? Okay, we have an exam question here. Cesium chloride and rubidium bromide are halide compounds of group 1 elements, okay? Now this is not stuff you don't really know yet. If you haven't learned it in school, not to worry, we'll be covering next. But just to show you guys that this is how compounds can sort of come up. So you got cesium chloride, rubidium, group 1 elements. Now you just gotta fill in this sentence. Cesium chloride has a formula what? A relative formula mass of what? That is that of rubidium bromide, and bonds that are what? Which words correctly complete gaps 1, 2, and 3? Okay, so you just need to, A, B, C, or D. I think you guys can see both on your computer, so I'm gonna leave the question here. So you can use the periodic table if you have it with you, but you don't really need it either. So might be a bit difficult if you've never seen a periodic table, but don't worry about it. Again, we'll teach it later. So if you can't do it, no worries. We haven't covered all the basics yet, okay? So let's see where everyone's at. So we got, a good mix of A's and C's. No one's saying B or D though. I see. Okay. Yeah. So in this case, I guess it would be good to see the periodic table. I'll take my word back on that. So basically, there is a bit of a mix-up with Ca and Cs. So what cesium is written as? So we know chloride is written as Cl. Ca or Cs. Okay, that's the main difference between A and, that is the only difference between A and C, it seems. Okay, we've got some B's and D's now. Okay, let's go through the answers. And the answer is, in fact, C. Great job. Okay, so let's explain this. Okay, going back to the question. So, trick. I know, I'm so sorry. So, cesium chloride. Cesium, in fact, is actually the symbol. The element symbol is Cs. So, Ca is actually calcium. I know they both start with Ca, but it's just that a long time ago, someone has already chosen calcium to be Ca, so cesium had to be Cs. And you'll find this on your periodic table, so you never have to guess these things, okay? So it's now the answer is either A or B. C or D, okay? Now, next we're going to look at number 2, a relative formula mass. So you don't need to look at the periodic table for this. All elements have different atomic masses, okay? So, okay, so we're comparing cesium chloride with rubidium bromide. The chances of them having the same relative formula mass is very slim. Not saying that it's impossible, but with the periodic table, you would see that they are definitely different. So it's already different. Now, even if you didn't know number 2, we can go to number 3. Bonds are, so in this case, the answer is ionic rather than covalent because chloride is a non-metal, whereas cesium is a metal, okay? Any bond between a metal and non-metal is always ionic. I know we don't usually use definite words in science, but it is always ionic for the sake of GCSEs, okay? If you're doing non-metal and non-metal, then it is covalent. Again, we'll cover these concepts in chemical bonds in a later lesson a few weeks from now. Okay? All right. That was a tough one. I hope everyone managed to get through that. Let's take a look at purity now. Let's get back onto their slides. And So, what is purity? Okay? Definition. There's a scientific definition, but also an everyday definition. Okay? So scientific definition is basically when there's a single element or compound only, not mixed with any other substance. The everyday definition, though, is different. It's basically the everyday definition is when a substance has nothing added. So let's look at pure milk, for example. Pure milk, okay? You might see in the supermarkets, oh, this is just pure milk, nothing else has been added in it, okay? But scientifically, pure milk is not actually pure. In milk, there's many different molecules and compounds mixed inside. It's just that it is naturally made from cows. So after the cows are milked, you put them inside the milk cartons, and it's pure in the everyday sense. But what the milk, if you put it in a machine that basically looks at what compounds are inside, you'll notice that it's not just made up of one element or one compound. It's made up of many different ones together. Okay, so you might see a lot of pure this, pure that in supermarkets, but they're not actually pure. Okay, even the water that you see in your taps, you might think that's pure in both ways. Okay, that's sort of a trick. It also depends. In some countries, they actually put extra things within your water, okay, to maybe like destroy bacteria and things like that. Yeah. So, yeah, pure in the scientific sense, that's what we're going to use it as, is basically a substance that has only one element or compound. For example, diamond, okay, it's made up of only carbon atoms. So the reason why we're talking about purity is basically if something is not pure, it's called a mixture. Okay, an impure substance. Impure means not pure, and they are made from different elements or compounds mixed together. So air, soda, coffee, they're all mixtures. Okay, mixtures of stuff. Air is not only made up of oxygen. If you didn't know, there's also things like nitrogen and hydrogen in the air, just in much smaller amounts than oxygen. CO2 is also in the air. Okay. Right. So pure substances versus mixtures. What you might see this often, where you might see this often in exam questions is to do with the states of matter questions. Okay, but we didn't cover it then. We're going to cover it now. So we're looking at heating cooling curves with changes of state, you know, boiling, melting, boiling, evaporation, what's that, freezing, and all that, okay? So for example, we're looking over here, we're looking at a curve. It's not the full curve, definitely, it's just a section, but just to show you guys, over here we have a cooling curve, part of it anyway. So it's basically a liquid at this point where the temperature is falling. It is a liquid. Yeah, over here, remember, the part that is changing, okay, this is the temperature, it's a liquid, but when it reaches whatever this substance is, when it reaches 40 degrees Celsius, it starts to freeze. Okay, it stays there because although it's getting colder and colder outside, even if it's getting cold outside, at 40 degrees Celsius specifically, the energy is put towards the freezing bit, okay? It's lost towards the freezing, and afterwards it becomes solid. So at this point, at the freezing point, what's happening is equilibrium, so like, not equilibrium, but like basically liquid is turning into solid, but you'll see both, okay? And then definitely below 40, you'll always see solid. So that's what happens with a pure substance. Now if you remember, we talked about impure substances lightly. Impure substances basically won't have a fixed temperature at which they change state. Okay? Here it was exactly 40 degrees Celsius. Over here it's between more like 30 to 40 degrees Celsius. Okay? It's not fixed. It's over a range of temperatures. Now that's important. Over a range of temperatures. Range of temperatures. Okay? So it's impure because there's more than one compound or molecule, whatever it is, in this substance. So each of these different compounds and stuff, they have different freezing points, for example, right? In this case. So that's why there is a range. Okay? So that's how you can tell whether something is pure or a mixture or impure. Okay? Now, why do we need things to be pure? Let's look at that. So pure substances have very well-defined physical properties. So things like boiling points, melting points, right? So electrical conductivity is very, very important. Purity is very, very important when it comes to electrical conduction. For example, copper in wires. Okay, copper is used to insulate so that when we touch a wire, we don't get electric shocks. Okay, so why do we need copper to be so pure? believe it or not, a lot of the materials that we find around us, they're impure. We need to go to factories to really extract the pure stuff out so that we can use them properly. Now, if we did not have pure copper for our wires, what would happen is that if the impure stuff could conduct electricity, we would touch a wire and we would get electric shocks. Okay, no matter how small or how even if it's 99% purity, whatever it is, that 1% can pass electricity onto you, and that's not what we want. Okay, so we want pure copper. Okay, so that it's completely insulating the wire. Okay, pure water is not a very good conductor because there are no dissolved blah blah blah. Yeah, that's okay. We don't need to look at that. Purity can also have an important impact on the chemical properties. So just now we looked at physical properties, now chemical as well. So pure substances can form predictable products from chemical reactions. So this is more important in things like labs, not even just scientific labs, like even when we're making anything. If you have used makeup before, you've seen your mom's sisters use makeup before, all those things, you don't just take them from the ground in the forest outside. You got to put things together. You want pure substances, okay? You don't want impure, dirty stuff inside your makeup that you're going to put on your face. Anything, even sunscreen, anything, right? Any product that you use. Now, the absence of impurity increases the reliability of experiments. So remember, we're looking at equations just now. If those things were not pure, we would have a ton of other things going on in the equation, and it would be very long. And basically, we would get a lot less product with a ton of other things in the way. Okay? So why is it important? It can be dangerous even in tiny, tiny amounts. For example, in food and in drugs. Drugs mean medicines, okay? If there were impurities in foods, which is why in the US, for example, you might have heard of something called the FDA, the Food and Drugs Association or something like that, I think. Basically, they make sure that the food is safe to eat, and even medicines as well, that they're all safe for human consumption within the USA, okay? And they look at all these products. So in food, if you have even if you have small amounts of impurities, it can cause gastric problems. Gastric meaning tummy. Okay, you might have your stomach might set. Remember, like sometimes if you eat food like chicken that is a bit too raw, or if you eat something that's a bit dirty, you might have some issues with your tummy. You might get upset, okay? You might have to end up going to the toilet a little more. So you guys might have gone through that before, and definitely it's not very pleasant, right? And sometimes in rare cases, they can lead to really fatal incidents. Fatal meaning someone's life, in the worst case scenario, may be taken because of an impurity. Medicines as well, you don't want all these toxic, harmful things inside. Now, these are some big words we have over here: carcinogens and teratogenic. Carcinogenic, you might have seen this in one of our bio classes before if you joined us, but carcinogenic basically means something that is RF means risk factor for cancer. I wanted to say causes cancer, but we don't want to ever be too sure about that because it's very hard to tell, but a risk factor, okay? So for example, smoking cigarettes is a very big one. Although a lot of research has shown that it's harmful and there are increased rates of lung cancer, there are still people out there who can smoke their whole lives and not get lung cancer. So it depends on your things like your genetics and stuff. So you're either really lucky or very unfortunate. Someone who might have smoked one time in their life might get lung cancer. So it's not one thing that causes cancer or anything in general. There's usually a multitude of factors, including your genetics, including your environment. Teratogenic is somewhat similar. Teratogenic is basically something that is a risk factor for causing a problem in fetuses. Okay, so this is more to do with moms and fetuses. So like when a woman is pregnant, for example, you might have heard that they don't really drink alcohol, they try not to smoke as well. If they do that, have that habit, because that can cause problems in children. So for example, if you drink a lot of alcohol during your pregnancy, what can happen is that it can cause some changes in the DNA in your baby, and it might result in a child who is born with something called fetal alcohol syndrome, FAS, and you might have a tiny head and you will have developmental problems, things like that. Okay. All right, so let's look at solutions and solubility a little bit, because we're going to cover this in mixtures later on. So solute, okay, these are some terminologies you need to know. Solute is a substance, usually in the smaller amount, okay, but don't worry about that. It's a substance dissolved in a oh dear, okay, sorry, solvent. This should be solvent, i.e. salt, example, salt or sugar, okay? So if you put sugar in water or salt in water, the salt or sugar will dissolve in the water. So in that case, the sugar or salt is considered the solute, okay? And the solvent will be the water. So solvent is the substance which the solute dissolves in, for example, water, okay? Look over here. And then what results when you put solute in a solvent and it dissolves, you get a solution. And this is where you might see the state symbols AQ. Okay, water itself is a liquid. Solute, in this case, it was a solid. So the solid plus liquid made an aqueous solution. Okay, aqueous means something was dissolved in the liquid. So that's the mixture of solute and solvent. For example, seawater, salt water, coffee. So now just a way to remember solute, solvent. I used to often get these things mixed up. Just a quick way to remember it until you guys get so used to it that you know what it means. So this is just a play on words, really. So if you guys imagine a thief has broken into a building, let's say a bank, and has stolen some money from the cash registers. Now he puts it in his bag, and you call that loot, right? He got his loot, and he put it on his back, and suddenly he heard the police cars coming. Okay, they're coming, and he was like, "Oh my God! Okay, I need to get out of here." But this loot is so heavy, I'm never gonna make it out of here. So what does he do? He sees a vent in the wall around him. Okay, a vent is like a hole in the wall. Usually you see that in your schools or whatever, and then you have sort of grills on them, and then you can sort of like pop them open. And what he did, he then put the loot inside the vent, okay, to hide it so that he can run off, and maybe he can come back and get it later, and maybe he won't get caught. So yeah, just a play on words, solute, solvent. So basically this guy put his loot into the vent, okay? So it's kind of like how you put solute in a solvent, okay? I hope that was a bit more fun to remember things. So more words. Soluble basically means when a substance can dissolve in the solvent, okay? Insoluble is, so this is talking about the ability, okay? Salt can dissolve in soluble. Now insoluble means cannot dissolve. So for example, if you put sand in water next, sand does not dissolve in water, okay? So that is insoluble. Okay, you can clearly see that there's a clear demarcation. It doesn't go all in. Saturated solution. Now this is a big term. So saturated solution is a solution with a maximum amount of solute dissolved in the solvent. You've got the maximum amount, for example, salt or sugar in the fixed amount of water that you've got. Okay. What happens? You get something that is in the middle of liquid and solid. It's kind of very sticky. You can tell that when you're stirring it in your beaker, it's a bit harder to push, not like water anymore. Okay, you might do this in your labs at some point. For example, seawater in the Dead Sea. So if you guys know about the Dead Sea is basically this body of water that has so much salt inside, where if you go inside and lie down, you will basically you'll be able to just float on top of it. Okay, it feels like you're on solid, but it's actually liquid. It might be interesting. You guys can Google it afterwards what the Dead Sea is. You got the maximum amount of salt in there. Okay. More definitions. So you need to know about some units. So maximum mass of a solute. So sometimes you might need to calculate the maximum mass of a solute to saturate 100 grams of water. okay, at a given temperature. So the units you might see in a question or that you might be asked to calculate is calculate something in grams of a solute in 100 grams of water. So different substances have different solubility. Sugar has a different solubility from salt, okay? You might need to put different amounts to saturate it, okay? Saturate also, I just want to say that when you put, for example, salt or sugar inside, when I say maximum amount, you might think that there will never be a maximum, but basically the maximum is when you look at the solution, you don't see the individual particles. That is okay. You know you are over the maximum when you start to see the actual salt and sugar, because it's not dissolving in the solution. So if you can actually see them, it means that it's not dissolving. So you have passed the saturation point. Okay? So solubility has some factors that affects them. So depending on whether it's a gas or a solid that we're talking about. So as pressure increases, so you guys know pressure is force over area. So if, for example, if we look over here, pressure is increasing, okay? As you gray lid into the beaker, the amount of area that these gas particles are in gets smaller, right? And because that gets smaller, and pressure increases, because of that, your force increases. That means it's hitting the walls and hitting each other molecule harder. Okay, and they become more soluble. So for gases, as pressure increases, they become more soluble. Now, if temperature increases, it's actually the opposite. Gases become less soluble in general. Not all the time with all these things. There are exceptions, but you don't need to know that now. As temperature increases, you can sort of imagine it like, if you have solids, liquids, and gases, it's more likely that something will probably come out as a gas rather than be dissolved in a liquid, right? Because they will be in a higher energy state that way. Because remember, when we think about temperature, we want to think about kinetic energy. Kinetic energy is the amount of energy something has, okay? And more energy means faster. And faster means more collisions, okay? So it's the opposite. Now, solids can also be soluble in stuff. It's more affected by temperature because it's not affected by pressure so much, because if you put a solid in water, you can't change the volume of a solid, right? Remember? So for solids, as temperature increases, solids become more soluble. Okay, so it's the opposite of gases. Don't worry, you can look at these slides later. It can be a bit difficult, but basically if you sit down and look at these sentences again after the class, just try to think about it logically in a way that makes sense to you, so that when it comes to exams, you're not ending up actually memorizing these things, and you're able to actually understand it. If you understand it, it is so much easier to go for exams, okay? Exam questions over here. So we've got multiple parts. So in an experiment to measure the solubility of potassium nitrate, the water in the beaker is heated and its temperature is measured. I'll give you guys 30 seconds to look at this whole question and sort of try to figure things out, and then I'll go through them. All right? So over here, this one should be fairly straightforward. Write down the temperature shown. So you've been given the image over here. So that's 40.5 degrees. I hope you guys notice that it's not 41. 41 is over here. Okay, so take note of that. That is 41. Part 2. Table 1 shows the results of this experiment. Use these results to calculate the mass of solid obtained and the mass of water removed. So if we look over here, you've got the mass of just the basin when it's empty, the basin plus the solution, and the basin plus the solid. So what's the mass of the solid? So to get that, you want to do 109 minus 98.5. Okay.